This will be the final screencast podcast in the kind of periodicity arrangement of electrons and atoms unit. So we're going to talk about periodic trends and some other stuff. So periodic trends are trends and patterns on the periodic table. So the first question is, what is the last written part of the electron configuration for elements in group 1? Well, if you look at elements in group 1 here that you can barely see, it's S1. In group 2, it's S2. And in groups 3 through 12, it is debatable. And in groups 3 through 18, it goes P1, P2, P3, P4, P5, P6. So what is the name for a group of individuals who are related to one another? It's called a family. We are family. So the groups are families because they have something in common. In fact, if we blow this up without a match. So everything underneath there has an S1. It means they have one valence electron. They're quite reactive. They love to lose that one valence electron. S2s have 2 valence electrons. When we skip over here, they have 3 valences, 4, 5, 6, 7, and 8. And those valence electrons tell you what they do. So things in group 1 love to lose 1 electron to become a 1+. These ones love to lose their 2 outer electrons to become a +2. Now, things under boron and carbon are a little bit different, but once we get to the nitrogen, phosphorus, and the arsenic, they love to gain 3 electrons because they're technically at the 5. They have 5 valence electrons, so if you go 5 plus 3, they get 8. 8's the magic number. And these ones have 6 valence electrons, and they like to gain 2 to become 8. And these ones have 7 valence electrons, and they like to gain 1 to become 8. And our noble gases, they're just boring. They don't do much. So let's just go on with the periodic trends. So when I look at the periodic table, I actually think of it in blocks, and that's how I have the squiggly chart in my head. I don't have it memorized. So I see these ones over here as the S groups. Again, S1 and S2. Then over here are the P's, so Seattle Police, and they're P1 through P6. D stands for department. Notice it's bigger because there's 5 spaces, remember, and they can hold 10 electrons, so there's 10 elements across. And then here are the F's, so Seattle Police Department flagellates. These green ones actually slide in there, which is a whole other trip of the mind, but I just like to look at it as blocks. The S block, the P block, the D block, the F block. We don't talk about the F's very much. Who wants to talk about an F? So periodic trends, we talk about atomic radius, and atomic radius is the radius of an atom. So as we go across the periodic table in a particular row, for example, just the top row, you can't skip rows here, the atomic radius gets smaller or it decreases. So if we look at this one, here it was lithium all the way across, and we ignore the noble gases because we do. So as you go across, this is kind of representing the atomic radius. It gets smaller. Totally weird. As more protons are thrown in the nucleus and more electrons are thrown around, you would think that the atom would become bigger, but it gets smaller. As you go down the columns, so if you go down like that way, so lithium, sodium, you can see as you go down, the radius does get bigger, and it should get bigger if you're adding more electrons and protons and you're adding energy levels. So as you go diagonally from the bottom left to the top right, the atomic radius gets smaller. So smaller, 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 stair steps up going to the right means smaller. So the one technically with the smallest radius on the periodic table is fluorine. Again, we ignore those noble gases. So the reason for the radius getting smaller. So atomic radius decreases across a row for several reasons. One, going across a row, both electrons are added to the same energy level while protons are being added. That's true, and you think it would be bigger, but the electrons are added in the same energy level. They are pulled closer to the nucleus due to a larger net pull from the addition of protons. So in essence, the electrons are within the same kind of zone as the other electrons, and the protons have such a much larger pull, a little bit like a strong magnet, that it pulls them in closer, hence the radius is smaller. So since they are pulled in closer, into the nucleus, the overall radius of the atom is smaller. So the reason for the radius trend going down. The radius increases as you go down a group of elements for several reasons. As you go down a group, more energy levels are added to an atom. Each energy level is successively further from the nucleus than the previous one. So this increase in energy levels provides a shielding effect, which in essence decreases the net pull that the protons in the nucleus have on the electrons. So less pull means that the electrons are added to larger energy levels that are further out from the nucleus, hence the radius gets larger due to this shielding effect and that they're in energy levels that are further out from the nucleus. So ionization energy is the energy needed to pull an electron away from an atom. It is in taking away electrons or gaining electrons that you get some exciting things in chemistry. So how much energy it takes to steal an electron from another atom is another way to look at it. So as you go across a row, the ionization energy increases. As you go down a group, the ionization energy decreases. And so as you go from bottom left to the top right, you get an increase in that. The atomic radius, I memorized that trend, and then the ionization energy and the electronegativity, which we haven't looked at yet. Those two trends are the opposite of atomic radius. So you really just need to memorize one and know the other trends are opposite, and it's opposite for a reason. So ionization energy increases for several reasons. Going across a row, the electrons are pulled closer into the nucleus due to a larger net pull in the nucleus. And since the electrons are added to the same energy level, it's more difficult to pull them away from there. So this larger net pull makes it more difficult, or it takes more energy to pull or steal an electron from the atom, thus an increase in ionization energy. Remember, the radius is small. It's small because it's really holding those electrons in tight, so it takes a lot of energy to remove one of those. And as you go down a group or a column, the electrons face a smaller net pull from the nucleus since they are added to successively higher energy levels, which means they're further out from the nucleus. And since the nucleus isn't able to hold the electrons in the atom as strongly due to the shielding of electrons in inner energy levels, they're easily removed or stolen. Hence, this takes less energy to ionize it, which means to remove an electron. So electronegativity is the tendency for atoms to attract electrons, or it's a love for electrons. So as you go across, this increases. This is just like the ionization energy, all this kind of the opposite idea. As you go down, it decreases. So electronegativity increases across because the net pull from the nucleus increases since the electrons are added to the same energy level. So there's more protons, it pulls them in more closely. So fluorine on the periodic table has a lot of electronegativity, has much more protons in the nucleus, and it can hold those electrons in its its second energy level shell pretty closely. So as you go down, electronegativity decreases, or the love for the electrons, because of the shielding effect. The nucleus has an effective smaller net pull since the electrons are added to successively higher energy levels. So atomic radius decreases as you go that way. Ionization energy and electronegativity increases as you go that way. So these two are the opposite of this one. That's what I remember. I just remember atomic radius is small up there. So anytime you take a step down, the radius gets bigger. Anytime over here you take a step down, the ionization energy gets smaller. So these are the types of questions you might see. So place these elements, Mg, where's my friend Mg, K, and Ca in order as follows. Ca. Ka. So increasing atomic radius. So it has to go from small to large. So magnesium has the smallest one because it's in a row up higher. And then between these two, the one that is further to the right is the smallest one, and then that one is the bigger one. So it goes MgCaK. Now if I ask you the opposite trends for the exact same things, you just flip-flop it because those values are the opposite. So increasing ionization energy. So Mg has the largest ionization energy, or the energy to steal an electron, because its electrons are held in closer than the Ka or the Ka. And the same with electronegativity. So a brief history of the periodic table. In the mid-1800s, there were about 63 elements known. Scientists noticed similar characteristics. In 1864, a German, Lothar Meyer, I don't know how you say that, was really the first to order the elements, but, have you ever heard of plagiarism? In 1869, this dude named Mendeleev attributed with seeing a distinct pattern amongst these elements, and some think this is true because his work was published and not Meyer's. But anyway, Mendeleev is credited with it, but they think Meyer actually did it first. There's a big story about Mendeleev. Mendeleev was born in Siberia. He was the youngest of 14 children. His dad died when he was young. His mom was left with all these children, and Mendy was her favorite. Ugh, to be the favorite. He ordered the table according to atomic mass, so their mass. And he noted that there were 7 periods, good for him, and he noticed that there were repeating periodic properties. In fact, he kind of made up the periodic table. He wrote the elements on like playing cards, and eventually he organized them, and that's how he came up with this. So the atomic mass idea is not correct. They're actually ordered by atomic number, which is number of protons. And then came Henry Moseley. He put the elements in order of atomic number and number of protons instead of mass. Groups are families because of similar properties, so there are columns. And there are trends going across the period, horizontal, but not similar properties. So groups on the periodic table, we talked about this before. Group 1, those are the alkali metals. Group 2 are the alkaline earths. Group 3 through 12 are the B groups, or the transition groups. So they add electrons to their d orbitals. They can transition them. That's why they're transition metals. Group 17, those are the halogens or the halides. Group 18, those are the noble gases. They're non-reactive because they have full S&P sublevels. They're not transitioning electrons anywhere. If you don't transition your electrons, you're not very exciting. So group 1, they like to form a +1 charge. They're almost always found with a coating of a metal oxide because they're so reactive. They react with oxygen in the air. They are highly reactive. They are soft metals. Some of them you can cut with a knife. How crazy is that? As long as you don't explode. And they are low density metals. Groups on the periodic table. So representative elements are the A grouped elements. So if you look on here, these ones are the A grouped elements, and their number in front of that A represents the number of valence electrons. We already talked about this. And the inner transition metals, the f orbitals, there's the lanthanides and the actinides. This sounds like some doctor's prescription. And I think we're good. That concludes our chapter. Happy holidays.